Little is simple and straightforward in gemology. Every established principle has an exception. This applies to gem classification as well. There isn't one way to classify gemstones. Rather, there are several. Each has its own purpose as well as exceptions that warrant close attention. Precious and semi-precious gems. For centuries, people have used the terms precious and semi-precious to describe gemstones. You'll still occasionally hear these terms today. However, this gem classification has so many exceptions it has no real value. For example, diamonds have traditionally been considered precious gems, yet some sell for $100 a carat. You can see them, with sufficient magnification, as accent stones on inexpensive jewelry. On the other hand, garnet gems have traditionally been considered semi-precious gems, yet some sell in excess of $1,000 a carat, 10 times the price of a low-quality diamond. Referring to a set of gem types as precious and all other gems as semi-precious can be misleading, since it implies precious stones have inherently greater value. Professional gemologists no longer use these terms. Consumers, be wary if you encounter these descriptions. Diamonds and colored stones. Gems are also divided into two categories, diamonds and colored stones. Some dealers use the shorthand color for colored stones. Gem cutters and dealers use this gem classification system for two main reasons. First, cutting diamonds requires special tools because these gems are harder than all others. With few exceptions, these tools aren't suitable for cutting colored stones. Therefore, gem cutters need two different sets of tools for handling both types of stones. Second, diamonds and colored stones are mined and distributed differently. Diamonds are one of the few gemstones with a consistent supply. Nevertheless, the diamond industry leads the general public to believe diamonds are incredibly rare. In fact, there are colored gems far rarer than diamonds. Why does this happen? A monopoly controls diamond sales and marketing. Those in charge are careful not to flood the market. Thus, diamonds maintain their value. This monopoly has also convinced the public that diamonds are the premier gemstones through excellent advertising. In this gem classification system, all diamonds, whether clear or colorless, are still considered diamonds. Conversely, a colorless sapphire or topaz is still classified as a colored stone. Gem classification: diamond, orange yellow diamond, natural, synthetic, and imitation gems. Another way to classify gems is as natural or synthetic. Natural stones, of course, form in nature. Stones created in labs can be subdivided further. Synthetic refers to materials that duplicate their natural counterparts. For example, synthetic emeralds, sapphires, and spinels share the physical and optical properties of the natural varieties. In many cases, distinguishing natural and synthetic stones is quite challenging. Haemocrete materials have no natural counterparts. This category includes the synthetic garnets gadolinium gallium garnet, GGG, and yttrium aluminium garnet, YAG. For a long time, gemologists considered cubic zirconia, CZ, a haemocrete gemstone. However, tiny CZ crystals not large enough to be used as gems have been found in nature. This discovery means CZ is a synthetic stone rather than a haemocrete. Natural and synthetic materials can share the same properties yet still have considerable differences. The main difference is rarity. A natural gem usually takes millions of years to form. Plus, many people feel natural stones have aesthetic qualities not found in mass-produced materials. Value is another difference. Since natural gemstones are rarer and take longer to form, they're more valuable than their synthetic counterparts. For this reason, Distinguishing between naturals and synthetics is an essential skill for gemologists. A simulant or imitation gem is any material presented as some of kind of gem. For example, a natural white topaz sold as a diamond is an imitation. If sold as a white topaz, it's a real, natural topaz. A CZ described as a cubic zirconia in a jewelry ad is not an imitation. In contrast, a CZ represented as a diamond is an imitation. Organic and inorganic gems. Another approach to gem classification is to separate gems into organics and inorganics. Organics refer to gems whose formation involves living organisms. Amber, for example, began as tree sap. Various mollusks create pearls. Hence, these gem materials are classified as organic. The term inorganic covers everything else. So, everything in the mineral world falls into the inorganic classification. One notable political exception arises in the US. In this country, a gemstone can only be classified as a mineral if it was created geologically in the earth. Thus, lab-created stones, even though they have the same properties as their natural counterparts, can't legally be described as minerals. For gem classification purposes, these lab-created gems have the same properties as their natural mineral counterparts. However, advertisements can't describe them as minerals. Gem classification, organic. This pendant features an amber gem containing fragments of fossilized organic matter. Crystalline and amorphous materials. Differentiating between crystalline and amorphous materials is another way to classify gems. The term crystalline refers to minerals comprised of a repeating pattern of crystals. The term amorphous refers to materials that have no set form or shape. Not all gems are crystalline. Amber and opal are good examples of amorphous materials. Glass, both natural and manufactured, is also an amorphous material. Amorphous materials can be both organic and inorganic. Examples of organic amorphous materials include amber and ivory. Inorganic amorphous gems include opal. Aggregates. The term aggregate applies to groups of small gems that form together. Aggregates form when the requirements needed for crystal formation, such as the presence of certain chemicals, heat, pressure, time, and space, aren't present for the necessary amount of time. Although an aggregate may look amorphous, it consists internally of thousands of microscopic crystals. The most common example of aggregate minerals is the chalcedony family, which includes agates and jaspers. These members of the quartz family share many common characteristics. So, these aggregates may have the same specific gravity and refractive index as a whole crystal of quartz but very different appearances. Rocks. Whereas crystals and amorphous materials have a single main ingredient, a mix of minerals comprise rocks. While not a gem material, granite is one of the most common and best-known rocks. If you look carefully at a sample, you'll see black, white, and gray bits all bound together. You won't see too many rocks in gemology. Lapis lazuli is perhaps the most well-known rock commonly encountered in the gem world. Gem classification. Granite. Minerals. Now we're getting into the heart of gem classification. The vast majority of gems are minerals. Both chemical makeup and molecular structure define the mineral species. Chemical makeup. Chemical makeup refers to the atoms contained within the mineral. Diamond, for example, has the simplest chemical makeup. Carbon, C, is the only element present. Corundum is composed of just two elements, aluminum, Al, and oxygen, O, expressed as the formula Al2O3. This means a molecule of corundum contains 2 aluminum atoms and 3 oxygen atoms. The chemistry of other gems gets more complicated. For example, Tourmaline's chemistry is expressed as Nali, Al3 Al6B3C6027O30, F. Molecular structure. Molecular structure refers to how molecules attach to each other. While you can see individual atoms, you can see the results of how they attach to each other in whole crystals. Diamonds form crystals that look like two pyramids attached at their bases. Quartz forms elongated crystals with 6 sides. These are results of their molecular structures. For example, imagine you have 2 sets of tiles. The 4-sided tiles will form one kind of design. The 6-sided tiles will form an entirely different set of designs. The 2 styles can't fit together. Each set makes up a different crystal system. Example, diamond and graphite. Used in pencil leads, graphite is very soft and black. The hardest substance in nature, diamonds are colorless. Diamond and graphite both have the same chemical makeup, pure carbon. So, what accounts for the difference in appearance and hardness? They're different arrangements of carbon atoms. The carbon atoms in diamonds are arranged in a tetrahedron pattern where each carbon atom is bonded to 4 other carbon atoms. This structure is incredibly stable, which accounts for a diamond's hardness. On the other hand, the carbon atoms in graphite are arranged in a chicken wire pattern. This structure is less stable. This makes graphite soft. When minerals share a chemical makeup but have different molecular structures, their molecular structures define the mineral type. Some minerals share a molecular structure but have different chemistry. In these cases, the chemical makeups define the mineral type. Mineral species and varieties. Throughout this article, we've discussed pure minerals. In nature, minerals commonly have impurities present in very tiny amounts, usually 3% or less of the crystal by weight. These impurities don't change the primary chemistry. Therefore, the mineral name, or species, doesn't change. They do, however, change some of the mineral's characteristics. So we use a subclassification called a variety. Changes in characteristics such as appearance can have a considerable effect on a gem mineral's value. Colors and varieties. Many pure minerals are colorless. Impurities give them color. For example, pure corundum is colorless. Add a bit of chromium and we call it a ruby. Add a bit of titanium and iron and we have a blue sapphire. Pure beryl is also colorless. Add a touch of chromium and we have an emerald. Add a bit of iron and you get an aquamarine. Just a tiny amount of impurities can make a mineral exceptionally valuable. Corundum and beryl are called mineral species. Their colored versions are varieties. Another very common species is quartz, with colored varieties such as amethyst, citrine, and smoky quartz. Garnet exceptions. There's always an exception or two. So, here we go. Not all minerals are colorless in their pure state. Garnet is one of the most obvious examples. Furthermore, there are several species of garnets as well as varieties. Garnets all share the same structure and a lot of similarities in their chemical makeup. However, they do have variations in chemistry. Each of these variations equals a new species of garnet. Here's an illustration that's not quite scientifically accurate but still helps explain how garnets vary. Look at your hand and pretend it's a model of a garnet molecule. All garnets have the same structure, the shape of your hand, and pretty much the same chemistry. The last joints of your fingers represent separate atoms. While most of the atoms remain the same, different atoms can reside in those places. If you change the atoms, the chemistry, you change the species. That's the rule. However, you can see that the shape of your hand has no changed nor